Tonight, we're going to explore something hiding in plain sight. Right now, at this very moment, there is a field filling every cubic centimetre of the universe. It's not switching on and off. It's not flickering. It is simply there, everywhere, all the time, with a value that never drops to zero. You can't see it. You can't feel it. No instrument in your house can detect it. And yet, without it, every electron in your body would be massless, racing through space at the speed of light, unable to form atoms, unable to form molecules, unable to form you. The entire physical world as you know it depends on this one field refusing to turn off. It's called the Higgs field, and the question isn't just what it does, the question is why it never stops doing it. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe genuinely helps the channel grow. It's a small thing, but it means a lot. Now, let's begin. Let me start with something you already know, even if you've never thought about it this way. You live inside fields. Right now, sitting wherever you are surrounded by them, immersed in them, and in some cases, made possible by them. Fields are not exotic, they are not rare, they are one of the most fundamental ideas in all of physics. And understanding what a field actually is, what it means for something to fill all of space at once, is the first step toward understanding why one particular field, the Higgs field, changes everything about the universe you live in. Start with gravity. You feel gravity right now. It is pulling you toward the center of the Earth. If you pick up a ball and drop it, gravity pulls it down. If you jump, gravity pulls you back. But here is the question that puzzled physicists for centuries. How does the Earth pull on you? You are not touching the center of the Earth. There is no rope connecting you to it. There is no physical contact between your feet and the core of the planet, thousands of miles below. So how does the force get transmitted across that distance? Isaac Newton described gravity mathematically in the late 1600s. His equations worked spectacularly well. They predicted the motions of planets, the trajectories of cannonballs, the behavior of tides. But Newton himself admitted something troubling. He could describe gravity, but he could not explain how it worked across empty space. How does the sun reach out across 93 million miles and pull on the Earth? Newton called this action at a distance, and he found it deeply unsatisfying. He wrote that the idea of one body acting on another through a vacuum without any intermediary was so absurd that no person with a competent faculty of thinking could ever accept it. And yet his equations worked, so people used them and tried not to think too hard about the mechanism. The answer came centuries later. The modern understanding is that gravity is not a force reaching across empty space. Instead, massive objects create a gravitational field that fills the space around them. The Earth does not reach out and grab you. The Earth creates a gravitational field, and that field exists at every point in the space surrounding the Earth. You, standing on the surface, are immersed in that field. The field is what pulls on you. The field is the intermediary. It fills the space between objects and transmits the influence of one massive body to another. This is a crucial concept. The field is not a thing floating in space like a cloud. The field is a property of space itself at every point. At every location around the Earth, the gravitational field has a value. That value tells you the strength and direction of the gravitational pull at that point. Move farther from the Earth, and the field value decreases. Move closer, and it increases. But the field is always there. It does not have gaps. It does not skip certain regions. It fills all of space continuously, extending outward in every direction, getting weaker with distance but never quite reaching zero. Now think about another field you encounter constantly, the electromagnetic field. When you turn on a light, you are using the electromagnetic field. When you listen to the radio, you are detecting oscillations in the electromagnetic field. When a magnet sticks to your refrigerator, the electromagnetic field is doing the work. When you see a rainbow, you are watching different frequencies of the electromagnetic field entering your eye. The electromagnetic field, like the gravitational field, fills all of space. It has a value at every point. It can be zero in some regions if there are no charges or currents nearby, and no electromagnetic waves passing through. But the field itself, the framework, the capacity for a value to exist at every point, that is always present. Light is not a substance travelling through space. Light is a ripple in the electromagnetic field, a wave, a disturbance propagating through the field at 300,000 kilometers per second. The field is the medium. The light is the wave in that medium. When you see sunlight streaming through a window, you are watching the electromagnetic field oscillating, its value rising and falling in a rhythmic pattern that your eyes can detect. So fields are familiar. You live with them every day. Gravity keeps you on the ground. Electromagnetism lets you see, lets your phone work, lets your heart beat through the electrical signals in your nervous system. These fields fill space. They have values at every point. They transmit forces between objects. This is the classical picture. But in the 20th century, physics went deeper, much deeper. Quantum mechanics changed everything about how we understand fields. In classical physics, a field is smooth and continuous. It can have any value at any point, and it changes smoothly from one value to another. But quantum mechanics revealed that at the smallest scales, fields behave differently. They are quantized. Their energy comes in discrete packets rather than continuous streams. A quantum field is a field that obeys the rules of quantum mechanics. And here is the remarkable thing. In modern particle physics, everything is a quantum field. Every type of particle you have ever heard of, electrons, quarks, photons, neutrinos, every single one is understood as a ripple or excitation in an underlying quantum field that fills all of space. There is an electron field that fills all of space. When that field is excited in a particular way, the excitation is what we call an electron. There is a photon field, which is the quantum version of the electromagnetic field. When that field is excited, the excitation is what we call a photon, a particle of light. There is a quark field, a neutrino field, a muon field. For every type of fundamental particle, there is a corresponding field filling the entire universe. This is not a metaphor. This is the literal framework of modern physics. The standard model of particle physics, which is our best and most precisely tested description of the fundamental building blocks of nature, is built entirely on quantum fields. Particles are not little balls bouncing around in empty space. Particles are localized excitations, vibrations, ripples in underlying fields that permeate everything. When physicists at the Large Hadron Collider smash protons together at extraordinary energies, they are not breaking open tiny shells to find smaller things inside. They are pumping energy into quantum fields and watching what kinds of excitations emerge. Different amounts of energy in different fields produce different particles. The particle is the excitation. The field is the thing that is always there. Now here is where most of these quantum fields share something in common. Something that seems obvious but turns out to be profoundly important. In their lowest energy state, in the state where everything is as calm and quiet as possible, most quantum fields have a value of 0. Think about what this means. Imagine you could take a region of space and remove absolutely everything from it. Every atom, every photon, every particle of every kind. You cool it to absolute 0. You shield it from every external influence. You create the most perfect vacuum possible. In that vacuum, the quantum fields still exist, because the fields are the framework of space itself. But most of those fields are sitting at their ground state, their lowest energy configuration. And for most fields, that ground state value is 0. The electron field, in empty space with no electrons around, has an average value of 0. The photon field, with no light present, has an average value of 0. This makes intuitive sense. If there are no particles, the field should be at rest. 0 excitation, 0 value, calm and quiet. But there is one field that breaks this pattern. One field that does not behave the way every other field behaves. One field whose lowest energy state, whose most relaxed, most stable, most natural configuration is not 0. The Higgs field. The Higgs field fills all of space, just like every other quantum field. It exists at every point in the universe, from the center of stars to the emptiest voids between galaxies. But unlike the electron field or the photon field, the Higgs field does not sit at zero in empty space. Its ground state, its lowest energy configuration, has a non-zero value. Everywhere, all the time, even in a perfect vacuum, even in the most remote, cold, empty region of space you could possibly imagine, the Higgs field is there, and its value is not zero. Let me make sure this is absolutely clear, because it is the single most important idea in this entire story. If you could somehow measure the value of the Higgs field at any point in empty space, you would not get zero. You would get a specific non-zero number. Physicists have measured this number. It is approximately 246 billion electron volts, expressed in the energy units that particle physicists use. You do not need to understand what that number means in technical terms. What matters is that it is not zero. It is a definite, measurable, persistent value that the Higgs field maintains everywhere in the universe. This is what physicists mean when they say the Higgs field never switches off. They do not mean that Higgs bosons are constantly being produced everywhere. They do not mean that some kind of Higgs radiation is showering through space at all times. They mean that the field itself, the underlying quantum field, has a background value that is permanently non-zero. It is always on. It is always there. It permeates everything. And this seemingly simple fact, this one field refusing to sit at zero, is responsible for some of the most fundamental features of the physical world. But let me slow down for a moment, because I want you to really understand what a non-zero field value in empty space means. Because it is strange. It is genuinely strange, and it should bother you a little bit. Think again about the electromagnetic field. In empty space, far from any charges or currents, the electromagnetic field is zero. There is no electric field, no magnetic field. Space is electrically neutral and magnetically quiet. If you placed a charged particle in that region, it would feel no electromagnetic force. The field is off, so to speak. Its value is zero and nothing happens. Now imagine a different situation. Imagine you are inside a capacitor between two large charged plates. One plate is positive, one is negative. Between the plates, there is a strong, uniform electric field. If you placed a charged particle there, it would feel a force. It would accelerate. The field is non-zero in that region, and that non-zero value has physical consequences. The particle behaves differently because the field is there. But here is the key. That electric field between the plates exists because someone put it there. Someone charged the plates. Someone set up the configuration. The field is non-zero because of an external cause. If you remove the charges, the field would go back to zero. The natural state of the electromagnetic field in empty space is zero. The non-zero value is artificial, imposed from outside. The Higgs field is not like that. Nobody set it up. Nobody turned it on. There are no Higgs plates at the edges of the universe creating a Higgs field between them. The non-zero value of the Higgs field is not imposed from outside. It is the natural state. It is the ground state. It is what the field does on its own when left completely alone. The lowest energy state of the Higgs field is non-zero. This is not something that was designed or engineered or triggered. It is a fundamental property of the field itself. The Higgs field prefers to be non-zero. It is more stable, more relaxed, lower in energy when its value is 246 billion electron volts than when its value is zero. This is deeply counterintuitive. For almost every other system in physics, the ground state is the most symmetric, most boring, most featureless state possible. A ball at the bottom of a valley, a pendulum hanging straight down, a spring at rest. These systems are at their lowest energy when nothing is happening, when everything is at zero. The Higgs field is the exception. Its lowest energy state is not at zero. Its lowest energy state is at a specific non-zero value. The ball is not at the bottom of a simple valley. The energy landscape is shaped differently for the Higgs field, and that difference in shape changes everything. Now this raises an obvious question. If the Higgs field is non-zero everywhere and always has been, why don't we notice it? Why can't you feel it? Why doesn't it show up in everyday experience? The answer is that you are completely immersed in it. You have always been immersed in it. Every measurement you have ever made, every experience you have ever had, every experiment ever conducted in the history of science has taken place inside the Higgs field. It is the background against which everything happens. You cannot step outside it. You cannot turn it off and see what the universe looks like without it. It is like asking a fish to notice water. The fish has never experienced anything else. Water is the medium of its entire existence. The fish does not feel wet because it has never been dry. Similarly, you do not notice the Higgs field because you have never existed without it. Consider an analogy. Imagine you lived your entire life at the bottom of an ocean. Everything you know, everything you have ever experienced, takes place underwater. The pressure of the water is always there, pressing on you from every direction. But you would not feel it as pressure. It would just be normal. It would be the default condition of existence. You would have no sense that something was pressing on you, because it had always been pressing on you, uniformly, from all directions, at all times. You would need to somehow get out of the water to realize it was there. And with the Higgs field, there is no getting out. There is no region of the universe where the Higgs field is zero. There is no experiment you can do in a Higgs-free environment, because no such environment exists. The field is universal. It fills everything. And because it is everywhere, uniform and constant, it becomes invisible. Its effects are woven into the fabric of physics itself. But invisible does not mean inconsequential. Far from it. The Higgs field's non-zero value has enormous physical consequences. It is the reason certain fundamental particles have mass. Without it, those particles would be massless, travelling at the speed of light, unable to form the structures that make up the physical world. The Higgs field does not just exist quietly in the background doing nothing. It actively shapes reality. It determines which particles have mass and how much mass they have. It determines which forces are short-ranged and which are long-ranged. It determines the basic architecture of the universe at the most fundamental level. And all of this happens because one field, out of all the quantum fields in nature, has a ground state that is not zero. One field that refuses to turn off. Let me frame this differently to make sure the enormity of it is clear. Imagine you are an architect designing a building. You lay out the foundation, you put up the walls, you install the floors and the ceilings and the windows. But then someone comes along and says, actually, there is an invisible substance filling every room in your building. You cannot see it, or touch it, or smell it. But it is there, everywhere, in every room, every hallway, every closet. And this invisible substance changes how everything in the building behaves. Doors that should swing freely now resist being moved. Objects that should slide effortlessly across floors now require effort to push. Some things are hardly affected at all, while others are profoundly changed. The substance is not blocking anything. It is not a physical barrier, but its presence changes the rules for how things move and behave inside the building. That is roughly what the Higgs field does to the universe. It fills everything, and its presence changes the rules for how fundamental particles behave. But here is where the analogy breaks down, and the real physics becomes even more remarkable. The Higgs field does not slow particles down like a viscous fluid. This is a common misconception that appears in many popular descriptions, and it gives the wrong impression. The Higgs field does not create friction. It does not resist motion. A particle moving through the Higgs field does not gradually lose speed the way a ball rolling through honey would. If it did, the universe would have ground to a halt long ago. Every particle would have slowed down and stopped. That is clearly not what happens. Planets orbit. Electrons circle nuclei. Particles fly through space at tremendous speeds. The Higgs field does not resist their motion. What the Higgs field does is something more subtle and more profound. It gives particles the property of mass itself. It does not slow them down. It makes them the kind of thing that requires a force to accelerate. A massless particle moves at the speed of light and cannot be slowed down or sped up. It has no inertia. A massive particle can move at different speeds. It resists changes in its motion. It has inertia. That that resistance to acceleration, that is what mass is. And for certain fundamental particles, that property comes from their interaction with the Higgs field. Without the Higgs field's non-zero value, those particles would have no mass. They would travel at the speed of light. They would never slow down, never stop, never form bound states, never build atoms, never build molecules, never build anything. The universe would be a fundamentally different place. It would be a universe of massless particles streaming through space at light speed, unable to clump together, unable to form structure, unable to produce anything remotely resembling the world you know. And this is not hypothetical. This is not speculation. This is the consequence of the mathematics that describes the standard model of particle physics. The equations are clear. If you set the Higgs field value to 0 in the equations, certain particle masses vanish. The particles become massless. The forces change their character. The universe becomes unrecognizable. The only thing standing between our universe and that massless, structureless alternative is the fact that the Higgs field has a non-zero value, the fact that it never switches off. Now, I should be precise about something important. The Higgs field does not give mass to everything. This is a very common oversimplification that you hear constantly, and it is misleading. The Higgs field gives mass to certain fundamental particles. It gives mass to the electron. It gives mass to the quarks. It gives mass to some of the force-carrying particles, specifically the W and Z bosons, which carry the weak nuclear force. It gives mass to the muon, the tau, and the neutrinos, though neutrino masses involve additional subtleties. These are fundamental particles, meaning they are not made of anything smaller as far as we know. They are the basic constituents, and for these particles, mass comes from their interaction with the Higgs field. But the mass of a proton, the mass of a neutron, the mass of the everyday matter that makes up your body and the chair you sit in and the planet beneath your feet, that mass is a more complicated story. Protons and neutrons are not fundamental particles. They are composite objects, built from quarks and bound together by the strong nuclear force. The quarks inside them do get their masses from the Higgs field, but the quarks are light, astonishingly light. The overwhelming majority of a proton's mass does not come from the masses of the quarks inside it. It comes from somewhere else entirely, from a mechanism that has nothing to do with the Higgs field. We will return to this in detail later, because understanding what the Higgs field does not explain is just as important as understanding what it does. For now, the critical point is this. This does not diminish the Higgs field's importance, not even slightly. Because if the Higgs field were not there, if its value dropped to 0, the quarks would become massless. The electrons would become massless. And while the strong force might still bind quarks into proton-like objects, those objects would behave very differently. The electrons, now massless and travelling at light speed, could not be bound into atoms. Chemistry would not exist. The periodic table would not exist. Water, carbon, oxygen, iron, none of the elements that make up the physical world would form in the way they do. The Higgs field does not account for most of your mass directly, but it sets the conditions that allow atoms to exist. It provides the mass of the electron, which determines the size of atoms. It provides the masses of the W and Z bosons, which determine the character of the weak force, which plays a role in nuclear reactions inside stars, which produce the heavier elements, which make up planets, which make up you. The chain of consequences that flows from the Higgs field's non-zero value is immense. And there is another subtlety worth pausing on. The fact that you cannot feel the Higgs field, that it is invisible and undetectable in everyday life, does not mean it has no observable consequences. Its consequences are all around you. Every time you pick up an object and feel its weight, you are experiencing consequences of the Higgs field. Every time you push something and feel resistance, inertia, that property is partially rooted in the Higgs field. Every time a nuclear reaction occurs inside the Sun, converting hydrogen into helium and releasing the energy that lights our solar system, the weak nuclear force is involved, and the weak force has the character it does because the W and Z bosons have the masses they do, and those masses come from the Higgs field. The field is invisible, but its fingerprints are everywhere. So here is where we stand. The universe is filled with quantum fields. Most of those fields, in their ground state, sit at 0. They are calm and quiet in empty space. But the Higgs field is different. It sits at a non-zero value everywhere, all the time. This is not because something is pumping energy into it. This is not because some external mechanism keeps it switched on. This is its natural state. Its lowest energy configuration is non-zero, and this persistent non-zero value, this background that permeates all of space, is what gives certain fundamental particles their mass. Without it, electrons would be massless. Without it, the W and Z bosons would be massless. Without it, the weak force would behave completely differently. Without it, atoms as we know them could not form. Without it, you would not exist. The Higgs field never switches off, because switching off would mean going to zero. And zero, for the Higgs field, is not the bottom of the hill. Zero is the top. The field sits where it sits because that is where energy is lowest. That is where stability lies. That is where the universe is most comfortable. Moving the field to zero would require enormous energy. It would be like pushing a ball uphill. The ball rolls back down. The Higgs field stays at its non-zero value because that is the valley. That is the resting place. That is where physics wants it to be. But this raises an obvious and deep question. Why? Why is the Higgs field's energy landscape shaped this way? Why is zero not the bottom? What makes this one field so different from all the others? Why does the universe have this one peculiar field with this one peculiar property that happens to make mass possible, and atoms possible, and chemistry possible, and life possible? The shape of the Higgs field's energy landscape is one of the most important features of our universe, and understanding why it has that shape, why the field settled where it did, is the next piece of this story. To understand why the Higgs field sits at a non-zero value everywhere in the universe, you need to understand something about energy landscapes. And the best way to understand energy landscapes is to start with something simple. Something you can picture in your mind before we apply it to the strange world of quantum fields. Imagine a ball sitting at the bottom of a bowl. The bowl is curved, smooth, and symmetric. The lowest point is right at the center. If you place the ball anywhere on the inner surface, it rolls down to the center and stays there. That is the stable point. That is where the energy is lowest. If you nudge the ball, it rolls back to the center. If you push it harder, it swings up the side, slows down, and rolls back to the center again. The center is the ground state, the equilibrium, the place where the system naturally wants to be. For most quantum fields in nature, the energy landscape looks exactly like this bowl. The lowest energy state corresponds to a field value of zero. The field sits at zero because that is the bottom of the bowl. If something briefly excites the field, pushing its value away from zero, the field oscillates back. It returns to zero. Zero is stable. Zero is where the energy is minimized. Zero is home. Now imagine a very different shape. Imagine taking that bowl and pushing the bottom upward from beneath, so the center rises into a bump. The shape now looks like a hat with a brim, or more precisely, imagine the bottom of a wine bottle. There is a raised point in the center and a circular trough, a valley, running around the base at some distance from the center. If you place a ball at the very top of the central bump, it sits there for a moment. Technically, it is at a point where the surface is flat, but it is not stable. The slightest disturbance, the tiniest nudge, and the ball rolls off the bump and down into the circular trough below. The center is a local maximum, not a minimum. It is the top of a hill, not the bottom of a valley. The true minimum, the lowest energy state, is the trough that circles the bump at a non-zero distance from the center. This is the shape of the Higgs field's energy landscape. Physicists call it the Mexican hat potential because of its resemblance to a wide-brimmed sombrero when drawn in 3 dimensions. The vertical axis represents energy. The horizontal plane represents possible values of the Higgs field. And the crucial feature is that the center of the hat, the point where the field value is zero, is not the lowest point. It is a peak, a bump, an unstable hilltop. The lowest energy ring, the trough running around the brim, corresponds to a non-zero field value. The Higgs field does not sit at zero because zero is not the bottom. Zero is the top. The field rolled off the hill and settled into the valley, and the valley is at a specific non-zero value. This is why the Higgs field has a non-zero value everywhere in the universe. It is not because something is forcing it to be non-zero. It is not because some mechanism keeps pumping energy into it to maintain that value. It is the opposite. The non-zero value is where energy is lowest. The field is at its most relaxed, most stable, most natural configuration when its value is approximately 246 billion electron volts. Pushing the field back to zero would require adding energy. It would be like pushing a ball uphill. Release it and it rolls back down into the trough. The field returns to its non-zero value because that is where the universe is most comfortable. But here is the question that should nag at you. Why is the energy landscape shaped like a hat in the first place? Why does the Higgs field have this peculiar potential with a bump in the middle? What determines the shape? The answer lies in the mathematical structure of the Higgs field itself. The shape of the energy landscape is determined by the parameters in the equations that describe the Higgs field. There are two critical parameters. One controls the curvature at the origin at the 0 point. For most fields, this parameter is positive, meaning the curvature bends upward at 0, creating a valley. 0 is the minimum. But for the Higgs field, this parameter is negative. The curvature bends downward at 0. 0 becomes a hilltop instead of a valley floor. The second parameter controls how steeply the energy rises at large field values, ensuring that the energy does not decrease forever as the field value increases. It creates the outer walls of the trough, preventing the field from rolling off to infinity. Together, these two parameters create the Mexican hat shape. A negative curvature at the origin pushes the minimum away from 0. A positive quartic term creates a restoring wall at large values. The result is a ring of minimum energy at a specific non-zero field value. The Higgs field rolls to this minimum and stays there. Now you might ask where these parameter values come from. Why is the curvature at the origin negative for the Higgs field and positive for every other field? This is one of the deepest unanswered questions in physics. The standard model does not explain why the Higgs field has the parameters it has. It simply takes those parameters as inputs, measures them from experiments, and uses them to make predictions. The predictions are extraordinarily accurate, confirmed to many decimal places by experiments at particle accelerators around the world. But the underlying reason for those specific parameter values remains a mystery. We know the energy landscape has the Mexican hat shape because experiments confirm the consequences of that shape. But we do not know why nature chose that particular shape for this particular field. What we do know is what happens when the field settles into the trough, and what happens is one of the most important phenomena in all of physics. It is called spontaneous symmetry breaking. Look at the Mexican hat shape again. The hat itself is perfectly symmetric. The trough forms a perfect circle around the central bump. Every point on that circle is at exactly the same energy. There is no preferred direction. If you placed a ball at the top of the central bump, it could roll in any direction, north, south, east, west, any angle whatsoever, and it would end up at the same depth in the trough. The hat does not care which direction the ball rolls. All directions are equivalent. The landscape has rotational symmetry. But the ball has to roll somewhere. It cannot stay at the top forever. Any tiny perturbation knocks it off, and once it rolls, it ends up at a specific point on the circle. It picks a direction. Not because that direction is special, but because the ball had to choose. The landscape was symmetric, but the outcome is not. The ball sits at one particular point on the trough, breaking the original symmetry of the hat. This is spontaneous symmetry breaking. The underlying laws are symmetric. The energy landscape treats all directions equally, but the actual state of the system, where the ball ends up, breaks that symmetry. The symmetry is hidden, not destroyed. It is still there in the shape of the landscape, but the physical state, the configuration the system actually occupies, does not reflect it. The Higgs field does exactly this. The equations governing the Higgs field have a deep symmetry built into them. This symmetry is related to the electroweak force, the unified description of electromagnetism, and the weak nuclear force. Before the Higgs field settles into its non-zero value, the equations treat the electromagnetic force and the weak force as aspects of a single unified force. The particles that carry these forces, the photon, the W boson, and the Z boson, are all massless and behave in a deeply symmetric way. The equations do not distinguish between them in the way we observe in nature, but when the Higgs field rolls off the hill and settles into a specific point in the trough, it breaks this symmetry. The electroweak symmetry is spontaneously broken. The unified force splits into two distinct forces with very different properties. The electromagnetic force carried by the photon remains long-ranged. The photon stays massless. But the weak force carried by the W and Z bosons becomes short-ranged because the W and Z bosons acquire mass from the Higgs field. The symmetry that once connected them is hidden. The underlying equations still have the symmetry, but the physical state of the universe, the state determined by the Higgs field's non-zero value, does not display it. This is not something that happened once and was finished. The Higgs field did not break the symmetry at some point in the past and then stop mattering. The symmetry remains broken right now, at this moment, because the Higgs field is still sitting in the trough. It is still at its non-zero value. The field's persistence is what keeps the symmetry broken. If the field somehow returned to zero, the symmetry would be restored. The W and Z bosons would lose their masses. The weak force would become long-ranged. The electromagnetic and weak forces would reunify. The universe would transform in ways that would make its current structure impossible. And this is one of the key reasons it matters that the Higgs field never switches off. It is not just that the field happens to be non-zero. It is that the non-zero value is actively maintaining the broken symmetry that gives the universe its current structure. The distinction between electromagnetism and the weak force, the masses of fundamental particles, the fact that atoms can form at all, these are consequences of a symmetry that is broken by the Higgs field right now. The field is not a historical artifact. It is a present and ongoing condition. Let me push the analogy a little further to make the symmetry breaking more vivid. Imagine a perfectly round dinner table with guests seated all around it. In the center of the table is a circle of wine glasses, one between each pair of adjacent guests. The setup is perfectly symmetric. Each guest has a glass to their left and a glass to their right, and there is no reason to choose one over the other. But eventually, someone has to pick up a glass. The first person to do so, say they reach for the glass on their right, breaks the symmetry. Now everyone follows suit, each taking the glass to their right. The original setup was symmetric. Every guest was equivalent. But the actual outcome, everyone drinking from the glass on their right, is not symmetric. One particular configuration was chosen, and once chosen, everyone else's behavior follows from it. The Higgs field is like that first guessed. The energy landscape is symmetric. The field could have settled at any point on the circular trough, but it settled at one specific point. And once it did, the consequences cascaded through all of particle physics. Certain particles got mass. Certain forces changed character. The symmetry was hidden, and the universe we observe emerged. Now I need to address something critically important, something that causes enormous confusion. The Higgs field and the Higgs boson are not the same thing. The Higgs field is the field. It fills all of space. It has a non-zero value everywhere. It is the thing that gives particles mass. It is always there. It never switches off. The Higgs field is the background, the ever-present condition of the vacuum, the permanent feature of empty space that shapes the laws of physics. The Higgs boson is something entirely different. The Higgs boson is a ripple in the Higgs field. It is an excitation, a disturbance, a temporary fluctuation above the field's background value. The Higgs boson is to the Higgs field what a wave is to the ocean. The ocean is always there, filling its basin, sitting at a certain level. A wave is a temporary disturbance that rises above that level and then subsides. The ocean does not need waves to exist. The ocean is there whether or not waves are present. Similarly, the Higgs field does not need Higgs bosons to exist. The field is there at its non-zero value, whether or not any Higgs bosons are present anywhere in the universe. This distinction is essential and too often blurred in popular descriptions. When physicists at the Large Hadron Collider announced the discovery of the Higgs boson in 2012, they were not discovering the Higgs field. They were confirming the Higgs field's existence by detecting its characteristic excitation. The field itself had been doing its work since the very early universe, giving mass to particles for approximately 13.8 billion years. The boson was the experimental proof, the signature, the fingerprint that confirmed the field was real and had the properties physicists had predicted. Think of it this way. If you are standing in a swimming pool, the water is all around you. It presses against you from every direction. It supports your weight when you float. It resists your motion when you try to walk through it. The water is the field, the permanent, ever-present medium that affects everything in it. Now, if someone jumps into the pool and creates a splash, the splash is a temporary disturbance. A wave radiates outward, ripples across the surface, and then fades. The splash is the boson. It appeared, it propagated briefly, and it dissipated. The water, the field, was there before the splash and remains after the splash. The splash confirmed that the water exists and has certain properties, like surface tension and viscosity. But the splash is not the water. The boson is not the field. At the Large Hadron Collider, physicists created Higgs bosons by slamming protons together at extraordinary energies. The collisions pumped energy into the Higgs field, creating brief excitations, ripples that we detected as Higgs bosons. These bosons are incredibly short-lived. A Higgs boson exists for roughly 1.6 times 10 to the negative 22 seconds before decaying into other particles. That is an astonishingly brief existence, far too short to observe directly. Physicists inferred the Higgs boson's existence by studying the particles it decayed into and working backward to determine that a Higgs boson must have been produced. The mass of the Higgs boson was measured at approximately 125 billion electron volts, divided by the speed of light squared, expressed in the units physicists use for particle masses. This mass is a property of the excitation, the ripple, not the background field value. The background field value, 246 billion electron volts, and the Higgs boson mass, 125 billion electron volts, are related but distinct numbers. The field value tells you where the field sits in the trough. The boson mass tells you how steeply the trough curves at that point, which determines how much energy is needed to create a ripple. This is a beautiful connection. The shape of the energy landscape determines both the field's resting value and the mass of its excitation. A steeper trough means a heavier boson. A shallower trough means a lighter boson. The fact that the Higgs boson has the mass it does tells us about the curvature of the Mexican hat potential at the point where the field sits. Experiments measuring the Higgs boson's mass are really measuring the shape of the energy landscape that governs the Higgs field. Now, let me make sure one more potential confusion is cleared away. When people say the Higgs field never switches off, they sometimes imagine that this means Higgs bosons are constantly popping into existence everywhere, some kind of steady rain of Higgs particles filling the universe. This is not what is happening. The Higgs field's non-zero value is a static background. It is not a stream of particles. It is a condition of space itself. Higgs bosons are rare, expensive to produce, and extremely short-lived. Under normal conditions, the universe does not spontaneously produce Higgs bosons. You need extraordinary energies concentrated in a tiny space to excite the Higgs field enough to produce one. That is why it took the most powerful particle accelerator ever built, the Large Hadron Collider, with its 27-kilometer ring of superconducting magnets and its proton beams traveling at 99.9999% of the speed of light, to create the conditions necessary to produce Higgs bosons in detectable quantities. The field is always there. The bosons are rare events. The field is the ocean. The bosons are the occasional splash. And it is the ocean, the ever-present background, that gives particles their mass, not the splashes. This distinction also helps explain why the Higgs field was so difficult to detect. For decades after its theoretical prediction in the 1960s, physicists knew the Higgs field should exist based on the mathematical structure of the electroweak theory. The theory required it. Without the Higgs field, the equations predicted massless W and Z bosons, which contradicted experimental observations. The W and Z bosons clearly had mass, large masses in fact, and the Higgs mechanism was the only known way to give them mass without destroying the mathematical consistency of the theory. So physicists were confident the field existed. But detecting a background field that fills all of space uniformly is extraordinarily difficult. You cannot detect it by contrasting a region with the field against a region without it, because there is no region without it. The only way to confirm the field's existence was to create its excitation, the Higgs boson, and detect that. And creating a Higgs boson requires concentrating enough energy in a small enough space to momentarily push the field above its background value at that point. This is roughly what the Large Hadron Collider does. Two beams of protons circulate in opposite directions around the 27-kilometer ring, accelerated to enormous energies. At specific points, the beams cross and protons collide head-on. The energy of the collision is converted into new particles according to Einstein's relation between energy and mass. If enough energy is concentrated in the collision, a Higgs boson can be produced. Out of the roughly 1 billion proton collisions per second at the Large Hadron Collider, only a handful produce Higgs bosons. They are rare events buried in an enormous background of other particle production processes. Finding them required years of data collection and extraordinary statistical analysis. The announcement on July 4, 2012, that both the ATLAS and CMS experiments had independently observed a new particle consistent with the Higgs boson was the culmination of decades of theoretical prediction, engineering, and experimental effort. Peter Higgs, along with François Englert and several other physicists, had proposed the mechanism in 1964. Nearly half a century passed before technology caught up with theory. The Large Hadron Collider was specifically designed, in large part, to find or definitively rule out the Higgs boson. And it found it, at a mass of about 125 billion electron volts. Peter Higgs and François Englert shared the Nobel Prize in Physics in 2013 for their theoretical work predicting the mechanism. But I want to emphasize again that the discovery of the Higgs boson was not the main point. The boson was the evidence, the field is the physics. The boson confirmed that the field exists and has a non-zero value everywhere. The field is what breaks the electroweak symmetry. The field is what gives particles mass. The field is what has been shaping the universe since the first moments after the Big Bang. The boson was the messenger. The field is the message. And that field, sitting quietly at its non-zero value in every cubic centimetre of the universe, never fluctuating to zero, never turning off, never taking a break, is what makes the physical world possible. Its persistence is not incidental. It is not a curiosity. It is the foundation on which the structure of matter rests. Let me return to a thought that connects back to the energy landscape. The Mexican hat potential tells us that the Higgs field settled at a non-zero value because that is where energy is minimized. The field rolled off the unstable peak at zero and found the stable trough at 246 billion electron volts. But this raises a haunting question. Is the trough the absolute lowest point? Or could there be an even deeper valley somewhere else in the landscape, a point of even lower energy that the field has not yet reached? This is a question with real physical consequences, and we will return to it. For now, what matters is what the Higgs field's non-zero value actually does, the work it performs every moment of every day, simply by being there. And to appreciate that, you need to understand something about the relationship between the Higgs field and the forces of nature. The electroweak theory, the mathematical framework that describes both electromagnetism and the weak nuclear force, has a deep symmetry built into it. That symmetry requires the force-carrying particles of the weak force, the W and Z bosons, to be massless. But they are not massless. They are among the heaviest fundamental particles we have ever measured. Something must be giving them mass without breaking the mathematical consistency of the theory. That something is the Higgs field. The non-zero value we have been discussing is not a curiosity. It is the mechanism by which certain particles acquire the very property that defines how they move through the universe. It is the reason the weak force behaves differently from electromagnetism. It is the reason the forces of nature have the distinct characters we observe. And understanding exactly how a background field gives mass to a particle is one of the most elegant stories in all of physics. The Higgs field settled where it did because that is where the energy landscape directed it. The Mexican hat potential, with its unstable peak at zero and its stable trough at a non-zero value, is the reason the field has the value it has. Spontaneous symmetry breaking is the reason the electroweak force split into the electromagnetic force and the weak force. And the permanent, ongoing presence of the Higgs field at its non-zero value is the reason that symmetry stays broken. The field does not switch off, because switching off means climbing uphill. The valley is where it is, and the universe we know exists because of it. But knowing that the field is there, knowing why it settled at a non-zero value, and knowing that it is distinct from the fleeting Higgs boson, still leaves the most important question unanswered. How, exactly, does a background field that fills empty space give mass to a fundamental particle? What is the actual mechanism? How does a particle interacting with an invisible, ever-present field acquire the property of inertia, the resistance to acceleration, the quality we call mass? This is not a vague or poetic question. The mechanism is precise. It is mathematical. It has been confirmed by experiment. and it is one of the most elegant pieces of physics ever conceived. Now we arrive at the heart of the matter, the mechanism. How does a field that fills empty space, a field you cannot see or feel, a field with a constant non-zero value everywhere, actually give mass to a fundamental particle? This is not a vague idea. It is not a metaphor. It is a precise physical process with precise mathematical underpinnings, and understanding it, even without the equations, reveals something extraordinary about how the universe works at its deepest level. To understand the mechanism, you first need to understand what mass actually is. Not in the everyday sense of how heavy something feels, but in the fundamental physics sense. Mass, at its core, is resistance to acceleration. When you push something and it resists changing its velocity, that resistance is inertia, and inertia is mass. A bowling ball is hard to push because it has a lot of mass. A tennis ball is easy to push because it has little mass. The more mass something has, the more force you need to change its motion. This is Newton's second law. Force equals mass times acceleration. Mass is the proportionality constant that connects how hard you push to how much the object accelerates. More mass means less acceleration for the same force. But here is the deep question. Why does a particle have the particular mass it has? Why does an electron have a mass of about 9.1 times 10 to the negative 31 kilograms and not some other value? Why does a muon, which is essentially a heavier version of the electron, have a mass roughly 207 times larger than the electron? Why does the tau lepton have a mass about 3,477 times the electron's mass? What sets these numbers? For a long time, physicists had no answer. Particle masses were just measured values plugged into the equations. Nobody could explain where they came from or why they had the values they did. But the Higgs mechanism provided a framework. It showed that for certain fundamental particles, mass is not an intrinsic property that the particle simply possesses on its own. Mass is a consequence of interaction. It arises because the particle interacts with the Higgs field, and the strength of that interaction determines how much mass the particle acquires. Let me build this up carefully. Start with a massless particle. A photon is the clearest example. Photons have zero mass. They travel at the speed of light. They cannot slow down, and they cannot speed up. From the moment a photon is created to the moment it is absorbed, it moves at exactly 300,000 kilometers per second. It has no rest frame. You cannot ride alongside a photon because nothing with mass can reach light speed, and a photon can never be at rest. This is what it means to be massless. You are locked at the speed of light, unable to exist at any other speed. Now consider a massive particle like an electron. An electron has mass. It moves slower than light. It can be at rest. It can move at different speeds depending on how much energy it has. It has inertia. It resists acceleration. Its behavior is fundamentally different from a photon's. The question is why? What makes the electron different from the photon? Both are fundamental particles. Both are excitations of underlying quantum fields. But one has mass and the other does not. What distinguishes them? The answer, according to the standard model, is the Higgs field. The photon does not interact with the Higgs field in the way that generates mass. The electron does. And that interaction, the coupling between the electron field and the ever-present Higgs field background, is what gives the electron its mass. But before I explain how this works for the electron, I want to focus on the particles where the Higgs mechanism is most dramatic, most necessary, and most revealing. The W and Z bosons. Because the story of the W and Z bosons is the reason the Higgs field was proposed in the first place. Without the W and Z bosons, there would have been no theoretical need for the Higgs field. They are the reason the whole framework exists. The W and Z bosons are the particles that carry the weak nuclear force. Just as the photon carries the electromagnetic force and gluons carry the strong nuclear force, the W and Z bosons carry the weak force. The weak force is responsible for certain types of radioactive decay. It is the force that allows a neutron to transform into a proton, emitting an electron and a neutrino in the process. This is beta decay, and it is essential for the nuclear reactions that power the Sun. Without the weak force, the chain of fusion reactions inside stars would not proceed the way it does. The weak force is also the only force that can change the flavor of a quark, converting an up quark into a down quark, or vice versa. It plays a role in the production of heavier elements in supernovae. It is fundamental to the workings of the universe. But the weak force has a peculiar property that distinguishes it from electromagnetism. It is short-ranged. The electromagnetic force, carried by the massless photon, has infinite range. It falls off with distance, but it never quite reaches zero. The electric field of a charged particle extends outward forever, getting weaker but never disappearing entirely. This is why you can see stars billions of light years away. The photons carrying the electromagnetic force travel freely across the universe without losing energy to the vacuum. The weak force is completely different. It operates only over incredibly tiny distances, roughly 1/1000th the diameter of a proton. Beyond that range, the weak force is effectively zero. It does not reach across atoms, let alone across space. It is confined to subatomic scales, operating only when particles are extremely close together. Why is the weak force short-ranged, while electromagnetism is long-ranged? The answer is mass. The W and Z bosons have mass, large mass. The W boson has a mass of about 80.4 billion electron volts. The Z boson has a mass of about 91.2 billion electron volts. These are heavy particles, roughly 80 to nearly 100 times the mass of a proton. And this mass is the reason the weak force is short-ranged. Here is the connection. In quantum field theory, the range of a force is inversely related to the mass of the particle that carries it. A massless force carrier, like the photon, produces a force with infinite range. A massive force carrier produces a force with a range that decreases as the carrier's mass increases. The heavier the carrier, the shorter the range. This is not a rough approximation. It is a precise mathematical relationship. The range of the weak force is about 10 to the negative 18 meters, and this corresponds exactly to what you would predict given the W and Z boson masses. So the W and Z bosons must have mass in order for the weak force to have the short range we observe. But here is the problem that tormented physicists for decades. The mathematical framework describing force-carrying particles, the framework of gauge theories, does not naturally allow those particles to have mass. When you write down the equations for a gauge theory, the force-carrying particles come out massless, automatically. Putting mass in by hand, just adding a mass term to the equations, destroys the mathematical consistency of the theory. The equations become nonsensical. They produce infinite probabilities and nonsensical predictions. The theory breaks. This was a crisis. Physicists knew the weak force was short-ranged. They knew this required massive force carriers. But they also knew that the mathematically consistent way to describe force-carrying particles, gauge theory, demanded those particles be massless. You could not simply declare the W and Z bosons massive without breaking the mathematics that made the theory work. This is where the Higgs mechanism enters. In 1964, several physicists independently proposed a solution. Peter Higgs in Edinburgh, François Englert and Robert Brout in Brussels, and Gerald Guralnik, Carl Hagen, and Tom Kibble in London all published papers describing essentially the same idea, approaching it from slightly different angles. The idea was that the W and Z bosons could start out massless in the fundamental equations, preserving the gauge symmetry and mathematical consistency, and then acquire mass through their interaction with a background field that has a non-zero value everywhere, the Higgs field. The mechanism works like this. In the fundamental equations, before the Higgs field settles into its non-zero value, the electroweak theory has a perfect symmetry. There are 4 massless force-carrying particles associated with this symmetry. They are not the photon, W and Z, that we observe. They are mathematical entities that mix together in the final theory. All 4 are massless. The equations are symmetric and consistent. Everything is mathematically clean. Then, the Higgs field settles into its non-zero value. Spontaneous symmetry breaking occurs. The symmetry of the electroweak theory is hidden, and when you work through the mathematics of how the 4 massless force carriers interact with the newly non-zero Higgs field, something remarkable happens. 3 of the 4 particles acquire mass. They become the W plus boson, the W minus boson, and the Z boson. The 4th remains massless. It becomes the photon. The mechanism by which this happens is sometimes described using a vivid analogy. Imagine a room full of people at a party, evenly distributed throughout the space. This crowd represents the Higgs field at its non-zero value. Now imagine a famous person walks into the room. As they try to move through the crowd, people cluster around them, drawn to them, slowing them down. The famous person acquires an effective inertia. They resist changes in their motion because the crowd interacts with them so strongly. That is like a particle acquiring mass from the Higgs field. Now imagine an unknown person walks through the same room. Nobody pays attention. Nobody clusters around them. They pass through easily, without resistance. That is like the photon, which does not interact with the Higgs field in the mass-generating way and remains massless. This analogy, while popular, is imperfect. It suggests the Higgs field creates friction or drag, which it does not. A more precise way to understand it is through the concept of coupling. Each particle has a specific coupling strength to the Higgs field. This coupling is a number, a parameter in the equations. The W and Z bosons have a strong coupling to the Higgs field. When the Higgs field takes on its non-zero value, this coupling translates directly into mass. The stronger the coupling, the greater the mass. The photon has 0 coupling of the mass-generating type, so it remains massless. What is actually happening in the precise language of quantum field theory is that the non-zero Higgs field value mixes with the fields describing the force carriers. The W and Z boson fields interact with the Higgs field background continuously as they propagate through space. This constant interaction changes their behavior. Instead of propagating like massless particles, zipping along at the speed of light, they propagate like massive particles, capable of moving at different speeds, possessing inertia, and having a rest frame. The mass is not added from outside. It emerges from the interaction between the particle's own field and the ever-present Higgs field background. And this is the crucial point. The mass is there because the Higgs field is there. Because the Higgs field never switches off. If the Higgs field went to 0, the W and Z bosons would immediately become massless. The weak force would become long-ranged. It would behave exactly like electromagnetism. In fact, the electromagnetic force and the weak force would become indistinguishable. They would merge into a single unified electroweak force carried by 4 massless bosons. The distinction between electromagnetism and the weak force, one of the most basic features of the universe as we experience it, exists only because the Higgs field maintains its non-zero value. This was confirmed experimentally. The W boson was discovered at CERN in 1983. The Z boson was discovered shortly after, also at CERN. Their masses were measured and found to be consistent with predictions of the electroweak theory incorporating the Higgs mechanism. Carlo Rubbia and Simon van der Meer received the Nobel Prize in Physics in 1984 for leading the experiments that discovered these particles. The discovery of massive W and Z bosons was powerful indirect evidence that the Higgs mechanism was correct, nearly 3 decades before the Higgs boson itself was observed. Now let me extend the story beyond the W and Z bosons to the fundamental fermions, the particles of matter. Fermions include quarks and leptons. Quarks come in 6 types, called flavors: up and down, charm and strange, top and bottom. Leptons include the electron, the muon and the tau, along with their corresponding neutrinos. All of these particles have mass, and for all of them, the Higgs field is responsible. But the mechanism for fermions is slightly different from the mechanism for the W and Z bosons. The W and Z bosons acquire mass because of how their fields interact with the Higgs field through the gauge symmetry structure of the electroweak theory. The details are dictated by the symmetry itself. There are relatively few free parameters. Once you know the Higgs field value and the gauge coupling constants, the W and Z masses are determined. Fermion masses work differently. Each fermion has its own separate coupling to the Higgs field, called a Yukawa coupling, named after the Japanese physicist Hideki Yukawa. The Yukawa coupling is a free parameter for each fermion. It is not determined by the gauge symmetry. It must be measured experimentally. The electron has a small Yukawa coupling, so it gets a small mass. The top quark has a very large Yukawa coupling, so it gets a very large mass, about 173 billion electron volts, making it the heaviest known fundamental particle. The muon has a Yukawa coupling roughly 207 times larger than the electrons, giving it a mass about 207 times larger. The tau has an even larger coupling. The formula is straightforward. A fermion's mass equals its Yukawa coupling multiplied by the Higgs field value divided by the square root of 2. Since the Higgs field value is the same for all particles, approximately 246 billion electron volts, the differences in particle masses come entirely from differences in their Yukawa couplings. The electron's coupling is tiny. The top quark's coupling is close to 1, the natural scale in these units. The neutrino couplings are incredibly small, giving neutrinos their almost negligible masses. This is simultaneously elegant and frustrating. It is elegant because one field, one background value, generates all the fermion masses through a single mechanism. It is frustrating because the Yukawa couplings themselves are unexplained. The standard model does not tell us why the electron coupling is the value it is. It does not explain why the top quark is so much heavier than the up quark. It does not explain the pattern of masses across the 3 generations of fermions. These couplings are inputs to the theory, not outputs. They must be measured, not derived. This is one of the great unsolved problems in particle physics. The Higgs mechanism tells us how particles get mass. It does not tell us why they get the specific masses they have. But let me be clear about what the mechanism does accomplish. Before the Higgs mechanism, there was no consistent way to give fundamental particles mass within the framework of gauge theories. You could not just declare a particle massive without destroying the theory. The Higgs mechanism provided a way to give particles mass while preserving the mathematical consistency of the electroweak theory. It showed that mass could arise dynamically from interaction with a background field rather than being put in by hand. This was a conceptual breakthrough of the highest order. Now let me address the particles that do not get mass from the Higgs field. There are 2 important examples, the photon and the gluon. Both are massless and both carry fundamental forces. The photon carries electromagnetism. Gluons carry the strong nuclear force. The photon remains massless because of how the electroweak symmetry breaks. When the Higgs field settles into its non-zero value, the symmetry breaking pattern is specific. It breaks the electroweak symmetry in a particular way that leaves one combination of the original force carriers massless. That combination is the photon. This is not an accident. It is a direct consequence of the mathematical structure of the symmetry breaking. The photon corresponds to a direction in the space of gauge transformations that remains unbroken. It is the force carrier associated with the residual symmetry, the part of the original electroweak symmetry that survives after the Higgs field does its work. That residual symmetry is ordinary electromagnetism, and the photon is its massless carrier. If the Higgs field had settled in a different way, if the symmetry had broken differently, the massless particle might not have been the photon. A different combination of force carriers might have remained massless, and the physics of our universe would be completely different. The fact that electromagnetism specifically survives as a long-range force is a consequence of the specific way the Higgs field breaks the electroweak symmetry. Gluons remain massless for a different reason. Gluons carry the strong nuclear force, which is described by a different gauge symmetry called quantum chromodynamics. The Higgs field does not break the symmetry of the strong force. The strong force gauge symmetry remains intact. As a result, gluons, the carriers of the strong force, remain massless. The Higgs field simply does not interact with gluons in the way that would give them mass. And yet, despite gluons being massless, the strong force is short-ranged. This seems contradictory. If massless force carriers produce long-range forces, why is the strong force not long-ranged like electromagnetism? The answer involves a completely different phenomenon called confinement. Gluons interact with each other, unlike photons. This self-interaction causes the strong force to behave in a way that is totally unlike electromagnetism. Instead of spreading out and weakening with distance, the strong force between quarks stays constant or even increases as you try to pull quarks apart. Quarks are permanently confined inside composite particles like protons and neutrons. The strong force is short-ranged not because its carriers are massive, but because of confinement. This is an entirely different mechanism from the Higgs mechanism, and it is unrelated to the Higgs field. I want to pause here and emphasize something about the W and Z bosons, because their story is especially important. Before the Higgs mechanism, the electromagnetic force and the weak force looked like they should be deeply related. Both are described by gauge theories. Both involve force-carrying particles. Both play roles in the interactions of fundamental particles. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg developed the electroweak theory, showing that electromagnetism and the weak force could be described as two aspects of a single unified force. All three shared the Nobel Prize in Physics in 1979 for this work. But there was an obvious problem. If the two forces are really aspects of the same underlying force, why do they look so different? Electromagnetism is long-ranged. The weak force is short-ranged. The photon is massless. The W and Z bosons are among the heaviest known fundamental particles. How can these be two faces of the same coin? The Higgs field answers this question. At the deepest level in the underlying equations, the electromagnetic and weak forces are unified. They are described by the same mathematical structure. The four force carriers are all massless, and the forces behave identically in terms of their range and strength. The asymmetry between them, the fact that one is long-ranged and the other is short-ranged, the fact that some carriers are massive and one is not, this asymmetry is entirely due to the Higgs field. The Higgs field's non-zero value breaks the perfect symmetry between the forces, splitting the unified electroweak interaction into the electromagnetic force and the weak force as we observe them. This means the difference between electromagnetism and the weak force is not fundamental. It is a consequence of the environment. The environment is the Higgs field, sitting at its non-zero value everywhere. In a universe where the Higgs field was at zero, there would be no distinction between the two forces. They would be one force with 4 massless carriers. The universe would look radically different. There would be no short-range weak force. There would be no massive W and Z bosons. Radioactive beta decay, the process that powers certain aspects of stellar nucleosynthesis, would behave entirely differently. This has profound implications for the very early universe. In the first fraction of a second after the Big Bang, the universe was extraordinarily hot. Temperatures were so extreme that the thermal energy was far greater than the energy scale associated with the Higgs field's non-zero value. Under these conditions, the Higgs field was not sitting in the trough of the Mexican hat potential. The thermal energy was enough to push the field back up to zero. The electroweak symmetry was restored. The W and Z bosons were massless. The electromagnetic and weak forces were indistinguishable. The universe existed in a symmetric phase where the Higgs field was effectively switched off. As the universe expanded and cooled, the temperature dropped below the critical threshold. The Higgs field underwent a phase transition, rolling off the unstable peak at zero and settling into the non-zero value in the trough. The electroweak symmetry broke. The W and Z bosons acquired their masses. The photon separated from the weak force carriers. The electromagnetic and weak forces became distinct. This happened roughly 1/1,000,000,000 of a second after the Big Bang, when the universe had cooled to a temperature of roughly 160 billion electron volts. This phase transition was one of the most consequential events in the history of the universe. Before it, the laws of physics were more symmetric, but could not support the structures we know. After it, the symmetry was broken. Particles had mass, forces had distinct characters, and the conditions were set for atoms to eventually form. The entire physical world as we know it crystallized from a more symmetric, more featureless state, because the Higgs field made a transition from zero to non-zero. And once that transition happened, the field stayed there. It never went back. The universe cooled further and further. The Higgs field remained at its non-zero value, and it has been there ever since. 13.8 billion years of a field sitting quietly in a trough, never switching off, and by doing so, giving the universe its structure. Let me bring all of this together. The Higgs field never switches off. It maintains a non-zero value everywhere in space, all the time. And this persistent background value is what gives mass to certain fundamental particles. The W and Z bosons acquire mass because the electroweak gauge symmetry is broken by the Higgs field, turning 3 of 4 massless force carriers into massive particles and leaving 1, the photon, massless. This is why the weak force is short-ranged and electromagnetism is long-ranged. Fundamental fermions, quarks and leptons, acquire mass through their Yukawa couplings to the Higgs field. Each fermion has its own coupling strength, and its mass is proportional to that coupling times the Higgs field value. The photon and gluon remain massless because they do not couple to the Higgs field in the mass-generating way. Every one of these masses depends on the Higgs field being there, being non-zero, being persistent. If the field fluctuated to zero, even briefly, even locally, the consequences would be catastrophic. Every particle's mass in that region would vanish. Electrons would fly apart from nuclei at the speed of light. Atoms would cease to exist. The very fabric of matter would dissolve. This does not happen because the Higgs field is extraordinarily stable at its non-zero value. The trough of the Mexican hat potential is deep. The field sits there firmly, undisturbed by the ordinary processes of the universe. But the fact that all of this, the distinction between forces, the masses of particles, the ability of atoms to exist, hinges on one field maintaining a non-zero value, should give you pause. It reveals something remarkable about the universe. The physical world is not built from particles with fixed, innate properties. It is built from fields interacting with other fields, and the properties we observe, mass, force range, the very identity of the forces themselves, emerge from those interactions. Mass is not a thing a particle has. Mass is a relationship between a particle's field and the Higgs field background. Change the background, and you change the mass. Change the mass, and you change everything. The Higgs mechanism is one of the most beautiful ideas in the history of physics. It shows that what appears to be a fundamental property of matter, mass, is actually an emergent consequence of symmetry breaking and field interactions. It unifies seemingly different forces into a single framework. It explains why the universe has the structure it has, and it all rests on one extraordinary fact. Somewhere in the deep mathematics of quantum field theory, one field has an energy landscape shaped like a Mexican hat. One field settled at a non-zero value. One field never switches off. And that is enough to build a universe. But there is something the Higgs field does not do. Something that, if you miss it, will leave you with a fundamentally wrong picture of where mass comes from. Because the Higgs mechanism we have just described, as elegant and powerful as it is, accounts for only a sliver of the mass you carry around every day. The number you see when you step on a scale, the weight of the chair beneath you, the heft of a stone in your hand, almost none of that traces back to the Higgs field directly. And the reason why reveals something just as profound about the universe as anything we have discussed so far. There is a statement you have probably heard many times. The Higgs field gives everything mass. It appears in headlines. It shows up in documentaries. It is repeated in popular science articles and television programs and casual conversations about physics. And it is wrong. Or rather, it is so incomplete that it becomes misleading. The Higgs field gives mass to certain fundamental particles, but most of the mass you encounter in your daily life, the mass of your body, the mass of the chair beneath you, the mass of the earth under your feet, does not come from the Higgs field. Not directly. And understanding this distinction is essential to understanding what the Higgs field actually does and what it does not do. Let me show you where the mass in your body actually comes from. Your body is made of atoms. Atoms are made of electrons orbiting a nucleus. The nucleus is made of protons and neutrons. So the mass of your body is, to an overwhelming approximation, the mass of the protons and neutrons inside your atoms. Electrons contribute very little. An electron has a mass of about 1/2000th the mass of a proton. So more than 99.95% of your body's mass comes from protons and neutrons. Understanding where the proton's mass comes from means understanding where almost all of your mass comes from. A proton is made of 3 quarks, 2 up quarks and 1 down quark, bound together by the strong nuclear force, which is carried by gluons. Now, the quarks inside a proton do get their masses from the Higgs field. The up quark has a mass of about 2.2 million electron volts. The down quark has a mass of about 4.7 million electron volts. Add up the masses of 2 up quarks and 1 down quark, and you get roughly 9.1 million electron volts. But the proton's total mass is about 938.3 million electron volts. The quarks account for less than 1% of the proton's mass. Less than 1%. The vast majority of the proton's mass, more than 99%, comes from somewhere else entirely. Where does the rest come from? It comes from energy. Specifically, it comes from the energy of the strong force interactions inside the proton. The gluons that bind the quarks together carry enormous amounts of energy. The quarks themselves are not sitting still inside the proton. They are moving at speeds close to the speed of light, confined within an incredibly small space, roughly 1 femtometer across, about 1 quadrillionth of a meter. Their kinetic energy is large. The gluon field between them is intensely active, with gluons constantly being emitted, absorbed, and even creating temporary quark-antiquark pairs that pop into existence and vanish again in tiny fractions of a second. The interior of a proton is a roiling, turbulent environment of quarks and gluons in constant, violent motion. All of this energy, the kinetic energy of quarks, the energy of the gluon field, the energy of virtual quark-antiquark pairs, contributes to the proton's mass through Einstein's most famous equation. Energy equals mass times the speed of light squared. Or equivalently, mass equals energy divided by the speed of light squared. Energy and mass are 2 sides of the same coin. The enormous energy contained within the proton, the energy of the strong force binding it together, manifests as mass. This is where more than 99% of the proton's mass comes from. Not from the Higgs field, from the strong force. This is worth sitting with for a moment because it overturns a common intuition. Most people think of mass as a property of the stuff inside something. You are heavy because you are made of heavy building blocks. And those building blocks are heavy because they are made of even heavier sub-building blocks. Mass comes from the material, from the substance, from the particles themselves. But that is not what happens inside a proton. The particles inside a proton, the quarks, are light. They account for almost none of the proton's mass. The mass comes from energy, the energy of motion, the energy of interaction, the energy of fields. Mass, at the most fundamental level, is not about stuff. It is about energy. The branch of physics that describes this, the theory of quarks and gluons and their interactions, is called quantum chromodynamics, usually abbreviated as QCD. It is one of the pillars of the Standard Model, alongside the electroweak theory that includes the Higgs mechanism. Quantum chromodynamics is extraordinarily difficult to calculate with because the strong force is, well, strong. At the distances inside a proton, the strong force coupling constant is large, which means the standard mathematical tricks that work beautifully for electromagnetism and even for the weak force do not work for QCD at low energies. Physicists have developed a technique called lattice QCD, where they simulate the strong force on powerful supercomputers by dividing space and time into a discrete grid and numerically computing how quarks and gluons behave. These calculations have successfully predicted the proton mass from first principles, starting with the quark masses, which come from the Higgs field, and the strong force coupling constant, and computing the resulting binding energy. The results agree with the measured proton mass to within a few percent. This is a remarkable achievement. It confirms that the proton's mass is overwhelmingly due to the strong force binding energy, not the Higgs mechanism. So the next time you hear someone say the Higgs field gives everything mass, you will know the fuller picture. The Higgs field gives mass to fundamental particles like quarks, electrons, and the W and Z bosons. But the mass of composite particles like protons and neutrons, which is the mass of nearly everything you encounter in daily life, comes primarily from the energy of the strong nuclear force. The Higgs field contributes about 1%. The strong force contributes the rest. But before you conclude that the Higgs field's contribution is negligible, consider what would happen if that 1% disappeared. If the Higgs field switched off and the quarks became massless, the entire structure of matter would change. Massless quarks would still be confined by the strong force. Proton-like objects might still form, but their properties would be different. The masses of hadrons, the composite particles built from quarks, would change because the quark masses affect the detailed dynamics of the strong force inside those particles. More critically, the electron would become massless, and a massless electron cannot be bound to a nucleus. This is the key point. Atoms exist because electrons orbit nuclei. The electron is bound to the nucleus by the electromagnetic force, and the size of the atom, the distance at which the electron orbits, is determined by a balance between the electromagnetic attraction pulling the electron inward and the quantum mechanical behavior of the electron, specifically its wave nature, pushing it outward. The electron's mass enters this balance directly. It determines the scale of atomic physics. The Bohr radius, the characteristic size of a hydrogen atom, is inversely proportional to the electron's mass. If the electron mass decreased, atoms would get larger. If the electron mass went to zero, the calculation breaks entirely. A massless electron travels at the speed of light. It cannot be captured into a bound orbit around a nucleus. There are no atoms. Without atoms, there are no molecules. Without molecules, there is no chemistry. Without chemistry, there is no biology. Without biology, there is no life. So the Higgs field's direct contribution to everyday mass is small, about 1% of a proton's mass. But its indirect contribution is total. Without the Higgs field, the electron has no mass. Without electron mass, there are no atoms. Without atoms, there is no complex structure of any kind. The Higgs field does not account for most of your mass, but it makes your existence possible. Every atom in your body depends on the electron having a non-zero mass, and that mass comes from the Higgs field. There is another way the Higgs field's absence would transform the universe, and it concerns the weak nuclear force. We saw earlier that the W and Z bosons owe their masses entirely to the Higgs field, and that those masses are what make the weak force short-ranged. Remove the Higgs field, and the weak force changes character completely. This would radically change nuclear physics. The weak force, in its current short-ranged form, governs the rate of certain nuclear reactions. It determines how quickly neutrons can convert into protons, and vice versa. These rates are crucial for the processes that build heavier elements inside stars. Change the weak force from short-ranged to long-ranged, and you change how stars burn, how elements form, how supernovae explode. The periodic table as we know it would not exist. The specific abundances of hydrogen, helium, carbon, oxygen, iron, all the elements that make up planets and people, these depend sensitively on the interplay between nuclear forces. Change one of those forces fundamentally, and you change everything downstream. The Higgs field, by giving mass to the W and Z bosons, and thereby making the weak force short-ranged, sets the conditions for nuclear physics to work the way it does. It sets the conditions for stars to burn hydrogen into helium through the specific reaction chains we observe. It sets the conditions for supernovae to produce the heavy elements that eventually become part of rocky planets. It sets the conditions for chemistry and for life. The Higgs field does not build atoms directly, but it shapes the environment in which atoms can be built. Now let me turn to something that sounds like science fiction, but is deadly serious physics. What would actually happen if the Higgs field did switch off? Not hypothetically, not as a thought experiment, but physically. Could it happen? And if so, what would the consequences be? The answer depends on the shape of the Higgs field's energy landscape, the Mexican hat potential we discussed earlier. The Higgs field currently sits in a trough at a non-zero value. The question is whether this trough is the absolute lowest point of the energy landscape or merely a local minimum, a valley that is lower than the hilltop at zero, but not the deepest point overall. Current measurements suggest something unsettling. Based on the measured mass of the Higgs boson, approximately 125 billion electron volts, and the measured mass of the top quark, approximately 173 billion electron volts, calculations within the Standard Model indicate that our current vacuum may be metastable. This means the trough where the Higgs field currently sits might not be the absolute lowest energy state. There might be a deeper trough at a much larger field value, separated from our current position by a tall energy barrier. If this is the case, then in principle, the Higgs field could quantum mechanically tunnel through the barrier. Quantum tunneling is a real phenomenon. Particles tunnel through energy barriers all the time. It is essential to nuclear fusion in stars, to the operation of certain electronic devices, to many processes in chemistry and biology. Tunneling through barriers is one of the defining features of quantum mechanics, and the Higgs field, being a quantum field, is subject to the same rules. If a tunneling event occurred, a tiny bubble of the new, deeper vacuum would form at some random point in space. Inside this bubble, the Higgs field would have a different value. The masses of all fundamental particles would be different. The forces would behave differently. The laws of chemistry would be different. The bubble wall would expand outward at the speed of light, converting everything it touched from the old vacuum to the new vacuum. Inside the bubble, the physics would be entirely different from what we know. Atoms, as we understand them, probably could not exist. Any structures, any matter, any life caught by the expanding bubble would be utterly destroyed. Not by violence or heat, but by a fundamental rewriting of the laws of physics. You would never see it coming. The bubble wall moves at the speed of light. No signal, no warning, no advance indication could outrun it. One moment, everything is normal. The next moment, the bubble wall passes through you and every particle in your body is suddenly governed by entirely different physical laws. You would not experience anything because the neural processes that constitute experience would cease to function before any signal could reach your brain. This sounds terrifying. But there is good news. The probability of such a tunneling event is spectacularly small. The expected lifetime of our metastable vacuum, the average time you would have to wait for a tunneling event to occur, has been calculated. The numbers vary depending on the precise values of the Standard Model parameters, but they are typically far longer than the current age of the universe. Some estimates put the expected lifetime at 10 to the power of hundreds of years. Others put it at 10 to the power of over 1,000 years. These are numbers so large, they make the age of the universe, 13.8 billion years, look like the blink of an eye. For all practical purposes, our vacuum is stable. The Higgs field will remain at its current value for a span of time that dwarfs any timescale relevant to human civilization, to stellar evolution, or even to the ultimate fate of the observable universe. There is also an important caveat. These calculations are done within the standard model. If there is new physics beyond the standard model, physics we have not yet discovered, it could change the shape of the energy landscape. New particles or new interactions could stabilize the vacuum completely, turning the metastable minimum into a true absolute minimum. Many extensions of the standard model, such as supersymmetry, have exactly this effect. So, the metastability question is not settled. It depends on whether the standard model is the complete story or just an approximation to something deeper. But the fact that the question can even be asked, the fact that the stability of everything, every atom, every star, every galaxy, every living thing, rests on the precise shape of one field's energy landscape, is one of the most striking features of modern physics. The Higgs field's non-zero value is not just important, it is the foundation on which the physical world is built. And the stability of that foundation depends on details of physics at the very edge of our current understanding. Let me now step back and reflect on what it means that the Higgs field never switches off. Because the implications go beyond particle physics, they touch on deep questions about the nature of the universe itself. First, consider what the Higgs field tells us about empty space. In everyday language, empty space means nothing is there. A vacuum is the absence of matter. But in modern physics, a vacuum is not nothing. A vacuum is the lowest energy state of all the quantum fields. And for the Higgs field, that lowest energy state has a non-zero value. This means that what we call empty space is not truly empty. It is filled with the Higgs field at its background value. The vacuum has structure, it has properties, it has energy. The Higgs field's non-zero value means that the vacuum itself is a physical thing with physical consequences. This is a profound shift in our understanding of emptiness. For most of human history, empty space was considered truly empty, a void, an absence, a nothing. Modern physics says otherwise. Empty space is a quantum state, a state with specific properties that determine how particles behave and how forces operate. The Higgs field is one of the most dramatic examples of this, but it is not the only one. Quantum fluctuations of all fields contribute to the energy of the vacuum. The Casimir effect, where two uncharged metal plates in a vacuum experience a measurable attractive force, is direct evidence that the vacuum has physical properties. The Higgs field's contribution is unique because it has a non-zero classical value, not just quantum fluctuations, but it fits into a broader picture where the vacuum is rich, complex, and far from empty. Second, consider what the Higgs field tells us about the origin of structure. The universe began in an extraordinarily hot, symmetric state. In the first trillionth of a second, all the forces except gravity were aspects of a more unified interaction. Particles were massless, the laws of physics were more symmetric and, in a sense, simpler. As the universe cooled, the Higgs field underwent its phase transition, settling into its non-zero value, breaking the electroweak symmetry and giving particles their masses. This was a moment of differentiation. Before the transition, there was uniformity. After the transition, there was diversity. Different particles had different masses. Different forces had different ranges. The raw material for complexity was created. In a deep sense, the Higgs field's phase transition was one of the universe's first acts of creation. Not creation from nothing, but creation of difference from sameness. The Higgs field introduced distinctions where none had existed. It made the electron different from the neutrino in a way that matters for atomic physics. It made the W boson different from the photon in a way that matters for nuclear physics. It transformed a featureless, symmetric universe into one with the varied properties necessary for structure, for chemistry, for stars, for planets, for life. Third, consider the sheer contingency of it all. The Higgs field has specific parameters that determine its behavior: the shape of the Mexican hat potential, the position of the trough, the coupling strengths to different particles. These parameters are measured quantities. We do not know why they have the values they do. If the Higgs field value were significantly different, if it were 10 times larger or 10 times smaller, the masses of all fundamental particles would scale accordingly. Chemistry would be different. Nuclear physics would be different. Stars might not burn the way they do. Planets might not form. Life as we know it might be impossible. The fact that the Higgs field value falls in a range that allows complex chemistry and stable atoms and functional stars is either a profound coincidence or a clue pointing toward deeper physics we have not yet uncovered. Some physicists invoke the anthropic principle, suggesting that in a multiverse with many different Higgs field values, we inevitably find ourselves in a region where the value allows observers to exist. Others search for a deeper theory that would predict the Higgs field parameters from first principles, showing that the values we observe are not contingent, but necessary. Neither approach has produced a definitive answer. The question remains open, one of the deepest puzzles in fundamental physics. Fourth, consider what the Higgs field teaches us about the relationship between fields and reality. We are accustomed to thinking of reality as made of things, objects, particles, stuff. But the Higgs field suggests a different picture. Reality is made of fields. Particles are excitations of fields. Mass is a relationship between fields. The properties we observe, the hardness of a rock, the weight of a person, the brightness of a star, these emerge from fields interacting with fields. The Higgs field is perhaps the most striking example because it demonstrates that even a property as seemingly fundamental as mass is not intrinsic to particles. It is a consequence of the environment in which particles exist. Change the environment, change the Higgs field value, and you change the mass. The particle itself does not change. Its coupling to the Higgs field is the same, but the mass it exhibits depends on the field value, which depends on the energy landscape, which is a feature of the universe as a whole. This is a deeply relational view of physics. Properties do not belong to objects in isolation. They arise from interactions between objects and their environment. Mass is not something an electron has. It is something an electron does, a consequence of how the electron field couples to the Higgs field background. In a universe without the Higgs field, the same electron field would produce massless excitations. The electron would still be an electron in some sense, the same quantum numbers, the same charge, but it would behave completely differently because the background it exists in would be different. Now let me address one final question that you might be asking. If the Higgs field is so important, if it shapes the fundamental laws of physics, if its non-zero value is the foundation of the physical world, why did it take nearly half a century from the theoretical prediction in 1964 to the experimental confirmation in 2012? The answer reveals something important about the difference between knowing a field exists and proving it. The Higgs field itself is undetectable by direct measurement. It fills all of space uniformly. You cannot compare a region with the field to a region without it, because no such region exists. The only way to confirm the field is to create its excitation, the Higgs boson, and that requires extraordinary energy. The Higgs boson has a mass of about 125 billion electron volts. No particle accelerator before the Large Hadron Collider could concentrate enough energy in a single collision to produce one. Previous machines, the Tevatron at Fermilab, the Large Electron-Positron Collider at CERN, searched for the Higgs boson and constrained where it could hide, but could not reach the energy needed to create it conclusively. The Large Hadron Collider was built, in large part, to settle the question once and for all. But energy alone was not enough. The Higgs boson decays in roughly 1.6 times 10 to the negative 22 seconds. It is never observed directly. It must be reconstructed from the particles it leaves behind, and those particles look almost identical to the debris from countless other processes that occur in every proton collision. For every collision that produces a Higgs boson, there are billions that do not, and the non-Higgs collisions produce similar-looking particles. Extracting the Higgs signal from this overwhelming background required years of accumulated data, extraordinary statistical methods, and detectors capable of tracking thousands of particles simultaneously with sub-millimeter precision. It required a global collaboration of thousands of physicists pooling their data and their expertise. The signal did not leap out. It emerged gradually, statistically, as a tiny excess in certain decay channels that grew more significant with each month of additional data until it crossed the threshold of discovery. This is why the Higgs boson was the last major prediction of the Standard Model to be confirmed. Not because the physics was uncertain, but because the experimental demands were staggering. The field had been doing its work for 13.8 billion years, shaping the masses of particles and the structure of forces long before any accelerator existed. The boson was simply the only way to prove it, and proving it required pushing technology to its absolute limit. The confirmation, when it came, was not just a discovery of a particle. It was a confirmation that the vacuum of our universe is not empty. It is structured. It is shaped by a field that has been present since the first trillionth of a second, and that has never once switched off. So here is where we end. The Higgs field never switches off because it has nowhere better to go. Its energy landscape, shaped like a hat with a bump in the center and a trough around the brim, ensures that the lowest energy state corresponds to a non-zero field value. The field settled there in the first trillionth of a second after the Big Bang, and it has remained there ever since. This persistent non-zero value breaks the electroweak symmetry, splitting a unified force into the electromagnetic force and the weak force. It gives mass to the W and Z bosons, making the weak force short-ranged. It gives mass to fundamental fermions, electrons, quarks, muons, taus, and neutrinos, through their individual Yukawa couplings. It leaves the photon and gluon massless because they do not couple to it in the mass-generating way. It does not directly account for most of the mass of protons and neutrons, which comes from the energy of the strong nuclear force. But by giving mass to the electron and to the quarks, it sets the conditions for atoms to exist, for chemistry to work, and for the physical world to have the structure it has. The Higgs field is not something that appeared once and stopped mattering. It is active right now. It is maintaining the broken symmetry right now. It is giving particles their masses right now. At this very moment, the Higgs field in the space around you, in the space inside you, in every cubic centimeter of the universe from here to the most distant galaxies, is sitting at its non-zero value, quietly and persistently shaping the laws of physics. If it flickered to zero for even an instant, the consequences would be immediate and total. Electrons would lose their mass, atoms would fly apart, the weak force would change its character. The chemistry that holds your body together would cease to function. The physical world would dissolve. It does not flicker. It does not waver. It does not switch off. It sits in its trough, stable and persistent, and by doing so, it holds the universe together. Not through force, not through energy, but through its simple, quiet, stubborn refusal to be zero. You will never detect the Higgs field with your senses. You will never feel it, or see it, or hear it. But every atom in your body owes its existence to it. Every breath you take is possible because of it. Every star that shines, every planet that orbits, every chemical reaction that sustains life, All of it depends on a quantum field that settled at a non-zero value 13.8 billion years ago and has never changed since. The Higgs field is the most invisible thing in the universe, and it is the reason the universe has anything visible in it at all.